in building, and that is in the line of sight, then it is 1.8 to 1.6 to 1.8. But if abstract is there in the form of tall buildings, abstracted buildings, they create a large exponent values. It goes from 4 to 6. These values are in the form of table, which is shown as this is here. It is the table. You can see it is the environment. This is the path loss exponent in the form of n. For the free space it is 2. For the urban area in a cellular radio 2.7 to 3.5. For this see the shadow urban cellular radio, it's 3 to 5, and is in building line of sight 3.26 to 1.6 to 1.8, and the abstract building it comes to 4 to 6, and the abstracted in the factories like then it's 2 to 3. So this is the log distance path loss model in practical link budget using the path loss models. Now we move towards the this is our next topic is log normal shadowing path loss. Log normal shadowing path loss. The topic is log normal shadowing path loss model. In previous we considered the this path loss model, because there is a long distance, there is some drawback in the form of the environment. Calculators. So we have also considering this in our environmental and values. So this model which we have seen in equation number 3, you have remembered, that is the given by path loss bar dv is nothing but PL dv, and this is equal to 10n log d2 d naught. Okay, so this is the previous equation 2. Consider that the fact that surrounding environmental calculator may be vastly different at the two different locations having the same TR separation. What we are saying to, this is our transmitter, it's transmit the these signals. Same user is transmitting the 3 different signals. But what happened when we transmit the first signal to the same separation distance between transmitter or receiver, there is a abstract, and the first receiver is catch these signals, and after that this signal is also reflected and it is comes to this or first user and the second receiver, and after that the line of sight is directly fell towards the receiver number 2, receiver number 1, and this is the receiver number 3. This is receiver 3, receiver 2, receiver. Only one user is there in the form of transmitter. It sends the three signals to the three different locations, but this three users is getting the same signals at the due to some environmental cultures. So it is insufficient to calculate this cultures in log distance model. So this model is having this drawback. So what we do now, what we have to leads to measure this signal which are vastly different than the average value predicted by this equation number 2, and measures have shown that at any level of distance d, the path loss PLD at the particular location, that means it is the random in nature and distributed log normally. So normal in a dB, normal in dB about the mean distance dependent value. So this is modified the equation, this PDL, we can write that PDL as it is, we have add the x sigma. This is the additional term is added in this formula, and this formula is adding by this now becomes as PL d naught, that is the reference distance d, and expand this formula, and x naught, this is the our PLD dV PL do not plus 10 n log d upon do not plus x naught equal to PLD dV is PLD plus xn. This is another important formula. Now if we include the antenna gain, include in the antenna gain, so it is the transmit received power is dVm, transmitted power dVm minus path loss distance dV. Here we include right here antenna gains included in PLD. See in this xn is 0 mean Gaussian distributed variable in dB with standard deviation sigma. This is the standard deviation sigma also in dB. So the log normal distribution described the random shadowing effect occur over a large measure location in cellular systems, where which occur over a large number of measured equations, and so many locations are having in different cities and different continental and different places. So we have the if we have transmit with the same, keeping the transmitter or receiver at the same separation distance d, then but we have the different level of clutter on this propagation path, then this phenomena is referred to as log normal shadowing. Simply, log normal shadowing implies that the measured signal level at a specific separation distance tr have a Gaussian normal distribution about the distance dependent means of equation number 2, that is the PLDB PL do not plus log and tan and log due to do not, where the measured signal level have the values in dB units. The standard deviation of the Gaussian distribution that described the shadowing also have the unit in dB. Thus the random effect of shadowing are accounted for using the Gaussian distribution, which lends itself ready to evaluations. In the close in reference distance, that is the do not, the path loss exponent, that is the n, and standard deviation, that is the sigma, and statistically described the path loss model for an arbitrary location having the specific TR separation, and this model may be used for the computer simulation and to provide received power level, to provide the received power level for random locations in communication system design and analysis. Random system design and analysis. If we want to check this by the graph, there are the two axes. The x-axis is having the log 10 d, y-axis is having the received power to transmit power in dV. There is a one main line. This line is denoted minus 10 log 10 d. There is a two closing reference distance. This is the standard deviation sigma from right and to left of this. Choose this arbitrary distance, and this is the our signal like this. This is called the x. This is the x. We write the x sigma. It is the x. X is the normal distribution, and this point which I have putting here, this is the normal actual received signals. This is the actual signals. Some of the actual signals are falling out of this range here and here. Some are falling close to these lines. So what happened? The log normal shadowing path loss, the deviation is shown by this. We having the certain function. After taking this arbitrary, if the signal received are outside of this reference received power, then we are also assume or calculated this within this permissible region. So in the practice, the value of n and sigma are computed from measured data using estimated path losses is minimized in a mean square error sense over a wide range of measurement location and transmitter or receiver separation. Then the value of path loss, reference value of path loss in equation number 4, in equation number 4, this is the our equation number 4. This is the PL, transmit power at distance d in dV. PL plus sigma n is equal to PL dV, that is described by PL d naught plus tan log n d2 d naught plus sigma n, normal distribution, or sigma is the mean deviation. So this mean deviation which we have seen, it is the equation number 4, is based on, this equation is based on equation this 4 is based on either close in reference measurements or on a free space assumption from the transmitter to do not. If it seen that the random variation about the mean path loss in dV are donated by shadowing at the specific TR separation is a random variable with a normal distribution in dV about the distance dependent mean. So the PR distance at d and the quality function Q function or the error function ERF may be used to determine the probability that the received signal level will exceed or fall below a particular level. So the Q function, the Q function is defined as Qj. Q of z is given by 1 upon root 2 pi e की power x square by 2 dx 1 by 2 is given by error function z upon root 2. And where the Qz is 1 minus Q minus Z. I having these two formula. This is equation 6, this is equation 7. So the probability that are received signal level will exceed a certain value, that is the gamma, can be calculated from the accumulative density function, which is as follows. Received power can be written as received power as distance if this gamma function, which is the certain values, that is the received power, should be increased this arbitrary constant gamma, then the quality function is now gamma minus received power divided by the mean sigma. Similarly, the probability that the received signal level will be